Have you ever just stopped and wondered why our world seems to play by two completely different rulebooks? I mean, on our scale, things are pretty straightforward, but you zoom way, way down, and you hit the quantum world, where everything gets weird. In this explainer, we're going to dig into a really fascinating new idea that might just bridge that gap and totally reshape how we see the universe. So, on the one hand, you've got the world you and I live in, right? The classical world. You toss a ball, it makes a nice, predictable arc. A car brakes, it comes to a stop. It's all governed by laws that just make sense to us. But on the other hand, you have the bizarre world of quantum mechanics. It's the law of the land for subatomic particles, and its rules are totally counterintuitive. It doesn't deal in certainties, but in a whole range of possibilities for what we might find when we look. So the billion-dollar question in physics is, how do you get from that world to our world? Right, so this is the heart of the problem. How do these two completely different realities connect? How does the solid, definite, classical world we experience actually arise from these fuzzy, probabilistic quantum foundations? You know, the standard explanation is that our world is really just the quantum world scaled up. The idea is that a process called decoherence, basically a quantum system interacting with its environment, smooths out all the quantum weirdness on a large scale. But a new model is proposing something much more radical. What this is really saying is that maybe quantum and classical mechanics aren't just different-sized versions of the same thing. What if they're two distinct theories that both bubble up from something even deeper, some unknown theory of quantum spacetime? That implies there's entirely new physics out there just waiting to be discovered. So if there's a divide, where is it? Well, this model suggests it's not just a slow, gradual fade from one to the other. It proposes there's a real physical boundary. And the key to this whole thing is a quantity called the Planck mass. Now, by our standards, it's minuscule. We're talking about the mass of a flea's egg. But in the world of particle physics, that is absolutely gigantic compared to something like an electron. And this is right where the story gets really interesting. So this isn't just a philosophical idea. The model puts forward a concrete physical dividing line. They call it a Heisenberg cut, right around the scale of the Planck mass. This is the place where the fundamental rules of the game are proposed to actually change. This chart lays it out perfectly. For particles way, way lighter than the Planck mass, standard quantum mechanics is king. For objects much heavier, good old classical mechanics works just fine. But right there in the middle, in that neighborhood around the Planck mass, that's where this new physics is supposed to kick in. Okay, so what is this new physics? How does it work? Well, the authors suggest a really elegant mechanism to bridge the gap, and it puts gravity front and center in a way we haven't seen before. The core idea is called gravitational self-decoherence. The thinking goes like this. As a particle gets more massive, its own gravity starts to mess with the fabric of spacetime in a way that makes it lose its quantum properties. It's like its quantumness, its coherence, literally leaks away into spacetime itself. Now, how on earth do you calculate something like that? They use a really clever mathematical trick. It's not a real thing, but a concept they use for the math, a virtual clone. Think of it as an identical twin of the particle that can only interact with the original through the force of gravity. So using this tool, they can model how that quantum information gets lost. They calculate the gravitational pull between the real particle and its clone. Then, and this is the key part, they mathematically remove the clone, which mimics how the particle's quantumness gets lost to these hidden parts of spacetime that we just can't see or measure. Now, here's where it gets really exciting. This isn't just some abstract idea. The model makes specific, concrete predictions that we can actually go out and test. This is where the rubber meets the road. To do that, we need a way to measure this quantumness, and we have one. It's a value called purity. If the purity is 1, you've got a perfect quantum system. If it's anything less than 1, it means the system has lost some of its quantum nature and is leaning more classical. And look at what the model predicts here. At just 20% of the Planck mass, a particle is still very quantum, a purity of 0.98. But as the mass gets bigger, as it moves through the Planck scale, you can see the purity drops off. It's not like flipping a switch. It's a gradual journey from the quantum world to the classical one. So how do we test this? There's a brilliant experimental design based on the classic Stern-Gerlach experiment that could do it. You use magnetic fields to split a particle's quantum state into 2 paths based on its spin. Then, you bring those paths back together and see if the particle is still perfectly quantum, or if some of that information got lost along the way. And here's the kicker. Standard quantum mechanics says the particle should come out perfectly, a probability of 100%. But this new model predicts something different. It says that as the particle's mass increases through that Planck-scale range, you should see larger and larger deviations from the standard prediction. And that's huge, because it means the model can be proven wrong. It's truly testable. Okay, this all leads to another really cool question. If a big object's overall motion is classical, does that mean every single trace of quantum mechanics is just gone from it? The second paper we looked at for this explainer dives right into this question. Can quantum rules still apply to the insides of a bigger object that's moving classically? The answer is pretty surprising. And the answer is a very nuanced yes. So while the object as a whole, its center of mass, starts behaving classically, its internal components can absolutely still be quantum. Think about the vibrations moving through a crystal lattice. Those can remain purely quantum. This actually helps explain some recent experiments where scientists have seen quantum effects in objects we thought were way too big for that sort of thing. This model gives us a framework to understand how both can be true at once. What I think is so compelling about this whole model is just how bold it is. It doesn't have a bunch of dials you can tweak to fit the data. It makes very clear, very specific predictions. As the authors basically say, when the experiments are done, it will either match the data or it's wrong. You have to respect that. That is good science. And that really leaves us with a pretty profound final thought. If this model turns out to be right, these experiments won't just be testing a new theory about the quantum to classical transition. They could be giving us our very first experimental window into the quantum nature of spacetime itself. And that would be a monumental step toward the ultimate goal of physics, a single, unified theory of everything.